Hey, I'm live. Okay, so are you all ready for the class on quantum field theory?
Back to the moon and beyond.
Okay.
For Ollie devotees, you probably recognize Bran Fortner, who really needs no introduction. So we had Bran speak to the symposia this past spring, and at lunch he complained to me. He says, I have spoken so many places, so many other CCRCs, and I have never spoken at the forest. I'm like, I can fix that. So please silence your phones or anything else that makes noise, and we'll get started.
Great, thank you. So we have a few minutes. How many of you have taken Astronomy 101? Oh, fewer than I would have guessed. How many of you liked it? How much did you remember? I teach Astronomy 101 at the great university in the Triangle, North Carolina State University. And what you're about to see over the next nine lectures is the course I wish I could teach. What I do is I don't talk a lot about the details that I think are unimportant. I try and get to the essence of it. So, when we teach a college course, we have a curriculum that we have to stick to. But here I don't. So I've gotten rid of all the extraneous stuff. I've focused on things that I think are the most important, the things that matter, the things I think any intelligent person should hear about. So what would you guys like to hear about over these lectures? I'm sorry? The Cosmic Universe, lecture 9. What else? Yeah, that's a different course. I teach a course called It's Almost Never Aliens. So invite me back. I taught that course at the Durham Public Library, and they thought I was there to tell them about UFOs and about how they're really living among us. And I says, no, I'm a scientist. Yeah, sorry. What else would you like to hear about?
Is the universe expanding?
I just had that lunchtime conversation. So let me ask you a question. Do you believe in evolution? Yeah. That over the last 100 years, we have discovered that nothing in biology makes sense except in the light of evolution. Evolution explains the entire framework. The Big Bang is the same for astronomy. Without the Big Bang, nothing makes sense. With the Big Bang, everything falls into place, just like evolution. And so for astronomy, Big Bang is no longer a theory. A Big Bang is fact. Just like in biology, evolution is no longer a theory. Evolution is fact. And I will be covering that in lecture 9. What else would you guys like to hear about? Yes. I don't cover that. Let me tell you why. There's so much material that we're certain about, and that's what this course is about. It's stuff that I think every intelligent person should know. Parallel universes is extremely speculative. I do talk about parallel universes in my course, The End of Everything, where we talk about the end of the universe. And there we do talk about, because that course is explicitly talking about theories that are very speculative. And it's fascinating. It's just not this course. What else would you guys like to? Yes. Yeah. That's the course I'm teaching in the fall at both Duke and NC State, called NASA. It's called Life on Europa, because both NASA and the European Space Agency are spending a majority of their science budget on the search for life. I didn't realize this. We've sent 48 probes to Mars looking for life. And so I'll be talking about that in that course. Not so much in this course. Yes? That's today's course. So what I'll be telling you in this course, well, it's divided into topics. So we've got the night sky coming up on the next lecture. Then we talk about the sun. We'll talk about the solar system. We'll talk about the Earth. We'll talk about galaxies. We'll talk about stars, stellar evolution, galaxies, and the cosmos. And each of those are kind of self-contained. And we'll tell you what the modern consensus is for each of those topics. We're going to skip all of the extraneous stuff and really focus on the fundamentals, the framework you must have if you want to be able to read science news and understand what they're talking about. What else would you guys like to hear about? Yes. Black holes, yes. We will be talking about black holes. That will be in lecture 6 and a little bit in lecture 7. Anything else? Okay, today's lecture, I didn't want to start right, I want to, I don't want to start until right at 1. Any other topics that you guys want me to cover? Comments? Yes. There's 9, right. Each lecture is fairly independent, but yes, they'll be consecutive. I'll go from small to large. So I'll go from the sun, the Earth, the sun, the solar system, stars, stellar evolution, in that order. But yeah, yes, every Tuesday here, right. Other questions? Yes. Yes. You will have to, because AI has permeated everything, you'll have to buy a blue book and write your answers in the blue book. No electronic aids. If I find you using your iPhone, you get a 0 for the course. Sorry, yeah. I tell my astronomy students, I give them all the answers to the tests. The problem is I give them 500 answers. If you memorize them, okay. Okay, so today's lecture, you can skip the other lectures. Actually, I prefer you don't. But this lecture you really can't skip because it's the background for everything else. The course is called Cosmic Curiosity, A Beginner's Guide to the Heavens. Do you ever wonder what the cosmos is and how we found it out? This is something that just doesn't seem to be covered in my astronomy textbooks. And it's something that fascinates me. How did we figure things out? Or perhaps you took Astronomy 101 and you need a refresher. You want to be able to read science or science news or nature and really understand what they're talking about, even though the reporters sometimes don't. It's when I read a science news article, you can identify right away, was this written by a scientist or a reporter? Because reporters typically write down what scientists tell them, which it's usually the truth, but it's never the whole truth. Okay, I'll get into that. So this course is for you. I'm only going to be talking about the most important things for each of the topics we're talking about. This is not comprehensive and not going to cover everything. It's just if I could teach a course like this to my undergrads, this is what I would teach. And the goal is to give you that sense of awe and wonder at the universe, which we always need. The universe has been around and will always be, actually not always. I teach a course on how the universe will end. And I also teach a course on how the universe began. So it hasn't always been around. But for our purposes, since we deal in terms of years and the cosmos deals in terms of billions of years, we can say to first order, yeah, it's always been around. We want to make sense of the press reports. And then what I would like to do is for some of the topics I'll be covering, I'll talk to you about what the ancients thought and then what modern people think. And the ancients were really smart. This is something that is often surprising, that people don't appreciate the fact that we have been fully human for, depending who you talk to, 50, 150,000 years. And you take somebody from 100,000 years ago and you raise them up in a modern era, they will be indistinguishable. Old people were smart. And I guess this is the right audience to say that. Yeah. Okay. So why should we care? we should care because at any age that we are, we want to be curious about everything. We'll have lectures on the night sky, our planet Earth, the sun, our solar system. The universe is a dangerous place. You often don't get this from science fiction, but it is. It's an extremely dangerous place. And so in these topics, we're talking about the night sky, our planet Earth, the sun, our solar system. We'll talk about the ways the universe is trying to kill us. Well, the sun is definitely trying to kill us. Asteroids are out to kill us. Our magnetic field is probably going through a reversal right now. That's going to try and kill us. There's lots of ways the universe is out to get us. And just because we've survived to the present point is no guarantee that we will in the future. This is known as the weak anthropic principle, if anybody cares. Anyway, I have a whole course on the weak anthropic principle. Then we'll talk about stars and stellar evolution. We need to know that not only for innate curiosity, but to understand how and why the sun will kill us. So our sun will most definitely destroy the Earth somewhere between 500 million and 1 billion years from now. And we've had a nice place to live for 4.5 billion years, so we have less time ahead of us than we did behind. So we're kind of in the late Middle Ages. Well, not even Middle Ages. We're kind of old age when it comes to our habitation on this planet. And then we'll talk about the Milky Way galaxy, we'll talk about the universe, and we'll talk about the ways the universe is trying to kill us with gamma ray bursts and death rays and everything else. So you can listen to this course either in terms of your innate curiosity or in terms of protecting yourself against everything that's out to get you. Here are the lectures. We've got lecture 1, which is the introduction, which is today. And lecture 2 will be the night sky, what we see when we look up. And I spent an entire lecture on it. It's much more subtle than you would appreciate. The next set of lectures will be the planet Earth, our sun, and our solar system. So sticking close at hand. The next lectures are about stars and evolution of the stars. And of course, our sun is a star. It's just kind of an average star. And then lectures 8 and 9 is the Milky Way galaxy and the universe. So I will send the PDFs of these slides to the powers that be, and they can make them available to you. And that way you can study them for the test, okay? So just to give you a framework, the night sky contains planets, it contains stars, it contains galaxies, and it shows you the universe. Our planet Earth is part of the solar system. The sun is part of the solar system. In terms of sizes, I'm going to use light travel time. So you can travel across the Earth in 1/10 of a second, more or less. You can travel across the sun in a couple of seconds. Our solar system contains the sun, the planets, and some debris. We'll talk about the debris. And the solar system is several light hours across. The stars, each star contains its own solar system. The stars themselves are light seconds apart, across, but they're separated from each other by light years, okay? Again, we went from seconds to hours to years. The Milky Way galaxy contains hundreds of billions of stars, and it's 100,000 light years across. And then the universe contains hundreds of billions of galaxies, and the galaxies are separated by millions or billions of light years. It's about 93 billion light years across. So it's big. By the way, if you have any questions, just raise your hand. I teach a lot on Zoom, and so I really appreciate actually having human beings in the audience. I assume none of you are AI. Anybody seen Kelly Norwood? I just saw it yesterday. Look her up on YouTube. It'll blow you away. Okay, anyway. So today's lecture. Today we'll start with 3 topics. What is objective reality? I actually like objective reality, even though a lot of people today don't believe in it. We'll talk about electromagnetic radiation for those of you that are how many astrophysicists in the crowd? Um, so for those of you that are not astrophysicists, this hopefully will be a framework so you can understand. For those of you with a science background, this will be review, but it still will be in the test. And we'll talk about things and forces, things that we assume everybody understands, but a lot of people don't. Like if I asked a random person, ma'am, what are the 4 forces in the universe? What would you say? You see? We think we know this stuff, and I assume students know this stuff, but most of the time they don't. And so this will be review. And then we'll do a summary of the other 8 lectures. We'll talk about a summary of the lecture on the night sky, our planet Earth, the sun, our solar system, the stars, evolution of stars, Milky Way galaxy, and the universe.
What we're looking for is how everything works.
Thank you.
What makes everything work? It has to do with curiosity. It has to do with people wondering what makes something do something. There's a way of looking anew, as if you never saw it before, for the first time, and asking questions about it as if you were different. And then to discover that if you try to get answers, that they're related to each other. And things that make the wind make the waves. And the motion of water is like the motion of air, is like the motion of sand. Things have common features. Turns out more and more universal. It's almost unbelievable. The truth is so remarkable, so amazing. It's incredible. Take the world from another point of view. It's curiosity. It's the where we are, what we are.
Just like a runner gets a kick out of sweating, I get a kick out of thinking. I can't stop.
It's curiosity.
So that was Richard Feynman, who was the greatest scientist of the 20th century, and in my opinion, and many other people's opinion. Bit of a jerk personally, but it's just I wish his brain still existed. He worked on the Manhattan Project, Los Alamos, and he died of cancer almost certainly because of his work there. So you look up at the night sky. Do you see galaxies? Do you see black holes? Do you see cosmic expansion? Do you see gamma ray bursts? Do you see neutron stars? No. What you see is dots of light. How did we get dots of light to all the things we actually know? How did we get to that, our current knowledge? And that's a miraculous story. And we'll be going over part of that story in this lecture series. And so what does it mean to understand the cosmos? And most scientists believe in 4 tenets of objective reality. This is actually revolutionary. What I'm about to talk about is why we exist in the modern world. The way we think about reality didn't really happen until starting with the 17th century, starting arguably with Galileo. So, number 1, there is an objective reality that's shared by all rational observers. Number 2, this objective reality is governed by natural laws. The universe obeys knowable principles, not necessarily known principles, but principles that can, in principle, be known. We believe this, okay? Reality can be discovered by systematic observation and experimentation. Science is the process of discovering and explaining this objective reality that exists independent of our existence. All things in nature must have a natural cause, and science believes in the uniformity of natural laws. Not only do we believe it, but we have essentially proved it. When I look at a galaxy 13.7 billion years old, or billion years away from us, 93 billion light years from us, and it obeys exactly the same physical laws that we do. We believe that the observable universe obeys the same laws for all space and all time, and evidence backs up that statement. That it's astounding that we live in a universe that obeys these. The most incomprehensible thing about the universe is the fact that it is comprehensible. What Albert Einstein was talking about is we can explain the universe with mathematical laws that the entire universe obeys. And there's no a priori reason why that must be so. We can imagine universes that don't follow these rules, and we see them all the time in our TV. Game of Thrones, Star Wars, Lord of the Rings, Harry Potter. These are universes that do not obey objective reality rules, okay? Well, we love them anyway, but they don't obey our rules. This is not our universe. Our cosmos is not magical. It's wonderful, it's awe-inspiring, but it's not magical. And that is what Einstein was trying to say. The fact that we live in a universe that isn't magical is just mind-blowing. The fact that we live in a universe that we can explain.
I like to think that what we're doing in science and in human exploration more generally is revealing fundamental truths that are out there, that are really part of the fabric of reality. They're not things which our brains process and impose on the outside world in order to organize our thoughts and our perceptions. But it's very hard to justify that perspective since, of course, everything we do, everything we think is processed through our brains. So it could be that our brains simply have this wonderful ability to find patterns and organize things in a way that allow us to tell a story about what's really happening out there. But that story is just something that our brains concoct to make sense of our perceptions. That's a real possibility. I don't know how to distinguish between the two, but I suggest we just keep going and try to make predictions and try to understand as much as we can.
So, how do we understand? And again, this gets back to the fact that the ancients were much smarter than we give them credit for. The Babylonians, 2000 BCE, 1000 BCE, were superb at observation. They had tables where they could predict the positions of the moon, the positions of the planets. They could predict eclipses. They were just geniuses when it came to what at the time was called astronomy, what today we would call observational astronomy, predicting the motions of the heavenly bodies. And then we talk about the Greeks. The Greeks really didn't care about reality. What they cared about were theories, and they had hundreds of theories of the cosmos, and you're familiar with several of those. We don't operate with either of those. What we operate in is what's called idea, predict, evidence. And this is a synthesis of the idea of observation and theory. That this emerged in the Renaissance. Before Galileo, we still had this separation between observation and prediction and what we would today call cosmology. What is the universe really like? And they really didn't talk to each other. To give you an example, you're all familiar with Nicholas Copernicus. And what you learned in school is that Nicholas Copernicus said that the sun is the center of at least the solar system, if not the universe. That's wrong, okay? The answer is a little more subtle than that. So Nicholas Copernicus most certainly wrote down equations showing that the calculations were easier if you assume that the sun was at the center and the planets went around the sun. But Copernicus didn't believe that that was reality. He believed that what he was doing was a mathematical trick. In other words, Nicholas Copernicus was not a Copernican, okay? So then you go forward 70 years, and we have Galileo Galilei, who looked at the universe with his telescope, and what he saw was a Copernican universe. And what he said was, this isn't a mathematical trick, this is reality. And for arguably the first time in philosophy, we have someone who tried to connect observation, theory, and reality, okay? And that's what we talk about, idea, prediction, evidence. New ideas emerge. We don't just want to predict the cosmos. We don't want to philosophize about the cosmos. We want to understand objective reality. And this is new, this is revolutionary, and this is what created the modern world.
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computations to nature, or we say compare to experiment or experience. Compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. In that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
We should send this video to our political leaders. I'm sorry, I was told not to be political. Okay, so objective reality. Let's say you have an idea, this is the way the universe is. We collect evidence. We have tools that extend the human senses. I can't find gamma ray bursts with my eyeballs. Just not going to happen. What evidence stacks up against that idea? And if it's okay, we provisionally say that's how the universe is, but only provisionally. Modern science is susceptible by definition to refinement, alteration, rejection. We will change our theory on the basis of contrary evidence. That's what a scientist does, or that's what a good scientist does. Scientists do not believe. We do not have people come up to me and say, you must have faith in this theory. It's like, yeah, no, that's not going to win any awards. You either prove or disprove the theory based on evidence, based on experiment. Tools that extend the human senses. We have electromagnetic radiation. We're going to talk about that in a minute. We have telescopes that look at light. I'm talking about the Vera Rubin Observatory. I have a course on the Vera Rubin if you want me to come back for that. Then we have the radio telescopes, most famously at Green Bank, West Virginia. We have infrared telescopes, most famously the James Webb Space Telescope. I have a course on that if you want me to come back and teach that course. We have ultraviolet satellites, X-ray satellites, gamma ray satellites. What is this? Why are you talking about all these things as electromagnetic radiation? Hold that thought. There are other ways we understand the universe that are a lot less common. We have the gravity wave detectors, which didn't exist until 2015. Gravity wave detectors is where the entire universe shakes when very, very dramatic things happen in the universe. In particular, you get taller and then shorter, and fatter and then skinnier based on two black holes colliding 4 billion light years away, billions of years ago. And we can detect those starting in 2015. We have neutrino detectors, particles that travel across the entire universe, then show up in Chicago, and we can detect them. And then we have new technology. We have new digital cameras. What I'm showing you there is a digital camera that's in the Vera Rubin telescope observatory. That camera that you're looking at costs $350 million. It's the world's largest and most expensive camera. And then, of course, we have supercomputers that do the processing. So we have unprecedented ways to understand the universe through these tools. So let's get back to electromagnetic radiation. Up until 2015, almost everything we knew about the universe came through electromagnetic radiation. Electromagnetic radiation is a wave of an electric field, you're all familiar with electricity, a magnetic field, you're all familiar with magnets, and if the electric field changes, it creates a magnetic field. If the magnetic field changes, it creates an electric field. And if those two fields kind of change together, it creates a wave that's independent of the source, and that wave travels through space. And you see those waves coming from these lights above us. They are producing electromagnetic radiation. What's the difference in electromagnetic radiation? Electricity, magnetism, is the frequency, how quickly it oscillates. The light that we see, what we call visible light, oscillates at a certain frequency. Gamma rays oscillate at a much higher frequency. X-rays oscillate at a slower frequency, but still much higher than light. Then we have ultraviolet, visible light, infrared light, microwaves, and then radio waves in order. So we go from extremely fast oscillation to extremely slow oscillation. One of the greatest breakthroughs of late 19th century science was the realization that all of these phenomena are the same. They only differ in frequency. Radio waves, gamma rays, X-rays, ultraviolet, visible light, infrared, microwave, they're all the same. It's all one big happy family, differing only in frequency, or alternatively only in energy. Okay? And we want to be able to observe the universe in each of these electromagnetic bands because we discover different things based on those bands.
Hi, I'm Emerald Robinson. In this What Is video, we're going to take a closer look at the electromagnetic spectrum. What we see as light is only a small part of the electromagnetic spectrum. The electromagnetic spectrum refers to the many types of radiation released from stars, including our own sun. Electromagnetic radiation travels in waves. Frequency describes how many waves per second a wavelength produces. Wavelength measures the length of an individual wave in meters. Scientists describe the electromagnetic spectrum as a long line. At one end lie radio waves, with the longest wavelengths and lowest frequencies in the spectrum. A single radio wave has the length of a football field. After radio waves come microwaves, which produce more energy due to shorter wavelengths and higher frequencies. Cell phones, radar, and microwave ovens use microwaves. Next comes infrared light. The sun, fire, living creatures, and other heat sources all produce infrared light. While we cannot see infrared light, we feel it as heat. Visible light occupies a narrow slice of the electromagnetic spectrum, nestled between infrared and ultraviolet light. Red wavelengths have the lowest frequencies and longest wavelengths of visible light. As you move from red through orange, yellow, green, blue, and finally violet, wavelengths shorten and frequencies increase. From visible violet light, we move into ultraviolet frequencies. Human skin produces vitamin D when exposed to ultraviolet light, but excessive ultraviolet light causes sunburns. Next, X-rays, which pass through soft tissue but not denser materials such as bone, making them valuable for medical tests. X-rays also have security applications such as airport baggage checks. Gamma rays produce even shorter wavelengths, higher frequencies, and more energy. In comparison to the football field-sized wavelengths of radio waves, gamma ray wavelengths are as small as atom nuclei.
For thousands of how-to and advice videos on any...
By the way, feel free to raise your hand, ask a question anytime. So we've got radio waves, microwaves, infrared, visible light, ultraviolet, X-ray, gamma ray. And different astronomical objects produce different amounts of each of these electromagnetic bands. And this is why we have satellites for each of these bands, so we can detect any electromagnetic band that the universe is producing. There are three features of the electromagnetic radiation that are really important for us to understand the universe. One is what's called thermal spectra, and we'll talk about that a bit. A thermal spectra is exactly what it sounds like. Any thick object in the universe, which includes all of you, produce a thermal spectra of radiation. We'll talk about that in a minute. Then we'll talk about emission and absorption lines. The way to think of emission and absorption lines is bar charts for materials. In other words, a particular element will produce electromagnetic radiation of very specific frequencies. If you find those frequencies, you know you were looking at carbon or hydrogen or helium. So in 1845, a famous physicist says, "Nothing is more certain than we will never know the composition of heavenly bodies." Nothing is more certain than we will never know the composition of heavenly bodies. 2 years later, other scientists discovered emission and absorption lines. 2 years later, we now knew that you could detect what things are made of from a distance by just looking at the electromagnetic radiation that came from them. Okay, so that's why emission and absorption lines are important. So thermal spectra enables you to detect the temperature of a distant body. Emission absorption lines enable you to detect the composition of distant bodies. And Doppler shift enables you to detect the motion of distant bodies. So these three features of electromagnetic radiation, thermal spectra, emission and absorption, and Doppler shift, are the primary tools for us understanding the universe. So let's talk about the thermal spectra, and let's go to William Herschel, who wanted to find out how much of each color the sun produced. And so what he did was he used a prism that was focused at the sun, and they looked at how much of each color it produced. And so what he did is he produced this line here by eye. This is a very, very famous graph. That line is, he said, when I look at a spectra of the sun coming through a prism, I see just a little bit of orange and red, quite a bit of green, and not so much of blue or ultraviolet, okay? And so this is the curve he draw by just guessing at the intensity of the different colors. So remember from that video, colors, each color in the visible light spectrum is a different frequency. So we see this very narrow band of electromagnetic spectrum, but within that narrow band, the colors are directly proportional to the different frequencies. And so he was able to map that. But then he was also created this second map. And what that second map was, he put a thermometer on the spectra that his prism generated. He put a thermometer on that spectra. And what the thermometer said was, yeah, we've got this increase, but the peak change in temperature with the thermometer happened in the part of the spectra that he could not see. How did that happen? There we go. So this peak from his thermometer measure says that there is a peak in something that's changing the temperature, but it's not visible to the naked eye. What William Herschel had discovered was infrared radiation. Radiation we cannot see with our eye, but we can measure with either a thermometer or an infrared camera. So for the first time, we had a correlation between two phenomena. One is heat and one is light, okay? And so then we roll forward quite a bit to Max Planck, who was able to mathematically prove that every thick object in the universe produces electromagnetic radiation of this exact shape, okay? Just like you see these shapes here. And so what this shape shows you is this object is producing a lot of blue, not much red. If I could see this object, visibly it would look blue. This object is at 7,000 degrees, which is pretty hot, we would call this blue hot, okay? As we go to lower temperatures, 5,000 degrees or 6,000 degrees, what we see is the shape is exactly the same, the height differs, and the peak differs. So it's something that's 5,000 degrees, it's mostly red, not much blue. So at 5,000 degrees, this would look red. At 6,000 degrees, it's fairly well balanced, and so you'd have as much blue, red, and green, and it would look white. Yes? No. I mean, you're correct. I actually use infrared lights, but that's it. Yes? Oh, I'm so sorry. I'll repeat the question. The question was, is this have anything to do with red being healing? And the answer is, I believe that's correct because I use red light for my feet, but this has nothing to do with that. And it has to do with how the various nerves absorb different frequencies of light, which is more physiology. Any of you buy a light bulb? Yeah, we've all bought light bulbs at some point. Have you ever noticed when you buy a light bulb, there's a number and a K? Right. You know what that number is? That is this number right here. If you bought a light bulb that said 6500K, it's going to look blue. If you bought a light bulb that says 3800K, it's going to look red. Those are two typical numbers you will see on light bulbs. When you buy a light bulb that says 3800K, back when they used to sell incandescent light bulbs, the filament of that light bulb would be at 3800 degrees Kelvin. Thermal spectra is universal throughout the entire universe. If you can measure the spectra, or alternatively the color, I can tell you the temperature of the object that generated it. Why are you people not glowing? You are glowing. If I had my infrared camera out, you would all be glowing in infrared, which we can't see with our eyes, but an infrared can see. And you are generating as much energy as a 100-watt incandescent light bulb. Y'all are little heat sources. And so I'm seeing you now through reflected light, but if we turned off the light and I popped up my thermal camera, we would see all of you in infrared light. That's the way we see the universe. We see the universe in all these different bands, most of which we can't see with our eyes, but our instruments can. And those instruments, by finding the different frequencies, tell me what the temperature of the object is. When you look up at the night sky, you see a blue star, that's a hot star, 7,000, 8,000 degrees. You look at the night sky and you see a red star, that's a cold star. That's going to be 3,000, 4,000 degrees, okay? Color tells you temperature. So that's thermal. Red, white, and blue, okay? I don't know if the founding of the country knew that those were spectral colors, but okay. So I'm talking about Kelvin. How many of you are familiar with Kelvin? Oh, okay, that's right. You're all dookies, okay? I should expect that. There's 3 temperature scales that are in widely use. The first one is called Fahrenheit. It's used in the United States, Liberia, and the Cayman Islands. End of story, full stop. The rest of the world uses Celsius. It's also known as centigrade. And Fahrenheit goes from 32 degrees Fahrenheit freezing to 212 boiling. Celsius goes from 0 Celsius to 100 degrees Celsius. By the way, the official term is Celsius. Centigrade is just what we call it because I don't know why. But the term we use is Kelvin. Kelvin is you take Celsius and you add 273 degrees, just because we want to confuse you. But when you're talking about 7,000, 8,000 degrees, the difference is in the noise. So when you see Kelvin, just assume centigrade.
In Fahrenheit, 0 was the freezing point of salt water and 96 the temperature of life. Celsius had 0 and 100 set at the freezing and boiling points of regular water, while Kelvin is just Celsius offset so that 0 is the coldest.
Got it? 10 seconds. Okay, so thermal spectra. Second one is emission absorption lines. These lines are barcodes. It has to do with electrons popping up and going down. I don't want to get into that. I don't want to put that on the test. They're useful because every element has unique frequencies. The spectra that I'm showing you for hydrogen is unique for hydrogen. Helium would have different lines, carbon would have different lines. So I can tell you what a star is made of, even if it's 93 billion light years away, and even if it's 13.7 billion years old. So, and the third one is Doppler shift. You are familiar with Doppler shift because we live with it day in and day out. Doppler shift is that change in frequency. The thing we live with day in and day out is the audio Doppler shift, but light does the same thing. So in sound, higher pitch approaches and lower pitch goes away. That is just so common. Light does exactly the same thing, except that because light travels much faster, light actually, you know what speed does light travel at? Yeah, the speed of light. Yeah. Light travels at the speed of light. What speed does gamma rays travel at? Speed of light. Yeah, people do that just to confuse you. Everything travels at the speed of light. But because the light is also Doppler shifted, we can detect whether something is approaching us or receding from us. Or in the case of the video you're seeing there, we can detect if something is moving around something else because the light will shift back and forth. Okay? So just think about this a second. Thermal spectra, I can tell how hot that thing is. Emission absorption, I can tell you what it's made of. Doppler shift, I can tell you how it's moving. And that's just an amazing amount of information that we can detect about things that are billions of light years away. So here's a solar spectra. This is the spectra of our sun. It has this thermal spectra. And so the surface of the sun is at 5,778 degrees Kelvin. This is why when you go to the grocery store and you see something that is daylight balanced, you'll also see something like 5,800 K or 5,500 K or sometimes 6,000 K. And that's because it's trying to do the same color balance that you would get from the overhead sun. Now, as the sun drops down the horizon, it varies, but that is the surface of the sun is 5,778 degrees. People sometimes get confused and say, isn't the sun millions of degrees? The core of the sun is over 10 million, usually about 15 million degrees. But the surface of the sun that we see, is at 5,878, and the peak radiation peaks in the band that we can see with our eyes. That is not a coincidence. Our physiology has adjusted so our eyes can see where there's the most electromagnetic radiation, okay? Just natural. And so if we grew up in a star that was much redder, our eyes would be downshifted to the ultraviolet section, okay? And you might notice that the spectra of the sun is a real mess. It's a real mess for two reasons. First of all, there's dozens, hundreds of elements and compounds and molecules in the atmosphere of the sun. In addition, there's dozens to hundreds of compounds and molecules and atoms in the atmosphere of the Earth. And so this is the red is what we detect on the surface of the Earth. The yellow is what we detect in outer space. But both of those have a lot of this weird stuff. That weird stuff is those thousands and thousands of absorption and emission lines because of all of the different chemicals that we have both in the atmosphere of the sun and also in the atmosphere of the Earth. Thermal spectra, absorption spectra, emission spectra. So, what is the cosmos made up? It's made up of things and it's made up of forces. What are the things that it's made of? Anybody? What's the universe made of? Right, puppy dog tails and atoms. Yes, it's made up of atoms. More specifically, you are actually made up of molecule. A molecule is where atoms combine. O2, for example, is a molecule. It's got 2 oxygen atoms. Molecules are made up of atoms. Atoms are made up of a nucleus and electrons. A nucleus has neutrons and protons. Electrons are things that whiz around and weigh almost nothing, okay? Just to give you some sense of perspective, if I had a grain of sand here that was the nucleus of an atom, the electron shell would be this building. Atoms are mostly empty space. In addition, and this will not be on the exam, neutrons and protons are not fundamental. They themselves are made up of smaller things called quarks. As far as we know, that's the bottom of the barrel. That's where the turtles stop. That the universe is made up of quarks and what we call leptons, which is electrons. So quarks and leptons is the entire universe. There are some people thinking that there's even more fundamental particles, but today's lecture and the next 8 lectures is the consensus knowledge, not things that crazy physicists are talking about. And the consensus knowledge is quarks and leptons, meaning electrons, is what the entire universe is made of. In addition, these things interact with each other through forces, of which there are only 4. Let me rephrase that. The canonical only 4. However, in 1999, we made a discovery that said these 4 forces cannot be the end all. There must be additional forces. And that discovery was the discovery of dark energy. That's correct. So those 4 forces, gravity, of course. If it wasn't for gravity, we would be having more fun here. We'd be floating around. Electromagnetism without electromagnetism would be really dark. And then we have 2 forces we don't normally interact with, the nuclear strong force and the nuclear weak force. These are the forces that bind the nucleus together, okay? And so they're very, very strong.
Hi, I'm Emerald Robinson. In this What Is video, we're going to take a closer look at atoms. All matter is made of elements, substances that cannot be broken down by chemical activity. An atom is the smallest particle of an element that retains the element's properties. Atoms are the building blocks for everything in the universe, including ourselves. People often think of atoms as the smallest possible forms of matter, but even smaller particles make up atoms. Each atom has a dense center called a nucleus. The nucleus contains neutrons, which have a neutral electric charge, and protons, which are positively charged. The number of protons in an atom determines an element's physical properties. No 2 elements have the same number of protons. Revolving around the nucleus like planets around the sun are negatively charged particles called electrons. Electrons and protons attract each other, so atoms usually have equal numbers of the 2 particles. Scientists assign atoms an atomic number and atomic mass unit. The atomic number is the number of protons present in the atom. For instance, a helium atom has 2 protons, so helium's atomic number is 2. Add the number of protons and neutrons in an atom's nucleus together, and you get the atomic mass unit, or AMU. A helium atom has 2 protons and 2 neutrons, so has a mass of 4 AMU. Electrons have almost no mass and are not included in AMU calculations. While an atom's number of protons remains constant, individual atoms can lose or gain electrons. Atoms with different ratios of electrons to protons are called ions. Atoms of the same element can also have extra neutrons. Scientists call atoms with extra neutrons isotopes. Despite having different neutron counts, isotopes retain their element's chemical properties because the number of protons remains constant.
For thousands of how-to and advice videos.
That will be on the exam. Okay, so here we got the atom. Just to summarize, the atom has a nucleus that contains neutrons and protons. Neutrons are neutral, protons positive charge. Then we have surrounded by electrons. Electrons, so by the way, we humans operate based on chemistry. Chemistry is where atoms combine and break apart. Chemistry is where the electrons of the different atoms combine and break apart. So we live basically in a world of electrons. The sun operates in a world of neutrons and protons. They operate at the nuclear level. And that's why we have nuclear reactors, nuclear fission, nuclear fusion plants that operate. But our day-to-day lives, we're basically just working with those electrons. And the number of protons define the element. And an element is so fundamental to what an object is. You know, hydrogen, helium, carbon, nitrogen, proton. And without getting down to the nucleus, you can't change what an element is. And so doing chemical reactions to change elements can never work. And so the alchemist's goal of changing base metal to gold could have never worked ever, no matter how hard they tried. Okay. The beauty of physics.
The fact that we humans, who are ourselves mere collections of fundamental particles of nature, have been able to come this close to an understanding of the laws governing us and our universe, it's a great triumph.
What we're looking for is how everything works and how everything is what makes everything work. Things that make the wind make the waves, and the motion of water is like the motion of air, is like the motion of sand. The fact that things have common features turns out more and more universal. But it's a curiosity as to where we are, what we are. What's the pleasure in physics is that, to me, is that as it's revealed, the truth is so remarkable, so amazing.
You asked me if an ordinary person, by studying hard, would get to be able to imagine these things like I imagine them. Of course, I was an ordinary person who studied hard. There's no miracle people. It just happens they got interested in this thing, and they learned all this stuff.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
When you're thinking about something you don't understand, you have a terrible, uncomfortable feeling called confusion. It's a very difficult and unhappy business.
Saying that you don't understand it, meaning I don't believe it, it's too crazy, it's the kind of thing I'm not going to accept.
So remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist.
I find myself trying to imagine all kinds of things all the time, and I get a kick out of it, just like a runner gets a kick out of sweating. I get a kick out of thinking.
Okay, that was the introduction. Now I'm going to do a very brief survey of the other 8 classes. The first 8 class, class next week will be on the night sky. We'll talk a lot about what the ancients knew about the night sky. The ancients knew the night sky a lot better than we did, okay? And what did they understand about the night sky? We'll talk about constellations. We'll talk about the ecliptic, not the ecliptic, elliptic. I always get those two confused. And when I tell my students to keep them separate, they're like, yeah. Okay, the ecliptic is a line on the night sky that the star, the moon, the sun, and all the planets are always on. The ecliptic. So it's very important, especially you're into astrology. We have, how did the sun and the moon and the planets move on the night sky? The ancients were wonderful at observation, at constructing ways to describe and predict the motion, but it wasn't until Galileo that we actually tried to map that onto reality. Then we talk about seasons. Why do we have seasons? Anybody? Why do we have seasons? I'm sorry? One at a time. Yes, why do we have seasons? Okay, so we have tilt of the earth. Who else? Why do we have seasons? Because of the orbit. Okay, so the orbit brings us closer to the sun and farther away, right? So the closer we are to the sun, the hotter it is. And so that means that when we're farther away, then it's winter and we're closer to the sun. How many believe that's right? Okay. So what's the tilt have to do with that? Anybody? I'm sorry? Yeah. So you can't hear the gentleman, but the gentleman's correct. And we're going to be going over this in detail in the next lecture. The interesting thing is the majority of people, of intelligent people, of Harvard graduates get this wrong. Okay? You got it right, sir. Ah, yes, that's why. That's why. It is confusing. It is confusing, and we'll go over this in detail. But like I said, it's just astounding how most people don't understand this. This is one of the reasons why this course exists, to the fundamentals that I think every intelligent person should know. By the way, for those of you that, I hope you're not shocked by this, the Earth is not the center of the universe. Even though it appears to be. You are standing here, the Earth is flat, and you are the center of the Earth. That's what it looks like. Science is the advancement of things that are non-obvious. Science is the things that violate common sense. The Earth is not the center of the universe. The sun is the center of the solar system, but it's not the center of the universe. We talk about constellations, how stars are grouped together. We talk about the ecliptic. We talk about stars. How many, I shouldn't have put on that. So how many stars do you think you can see in the night sky for those of you that didn't see that slide? How many stars? 5 million? 10 million? 10 billion? The number of stars you can see in the night sky, there's 400 billion stars in our galaxy alone, and 400 billion galaxies. 400 billion stars, of which in a clear night in a dark sky, not in Raleigh, not here, because here we can see a few hundred, but in the darkest skies you can imagine, you can see 3,000. 3,000, as you can see in this picture, looks infinite. But the brain just has trouble conceiving of so many stars. And we'll talk about the distance to these stars. Now, the thing that back in ancient times, back when we were young, so before electric lights, okay, what you had for entertainment was the night sky. The night sky was your Netflix. And so ancients were extremely familiar with the night sky. It was obvious to them that the night sky rotated. I bet you undergraduates today don't even realize that the stars move. Because they look up, they see the stars, they think they're fixed, they're not moving. But if you spend any amount of time looking up the night sky, you can see that motion. It's just very slow. As you can see with these time-lapse images. Lecture 3 is about our planet Earth. You think, well, hey, I live on the planet Earth, there's nothing to talk about. Well, there is, because we talk about the fact that it's a sphere, kind of, the fact that it rotates once every 24 hours. So if it rotates once every 24 hours, why don't I fly off? This is why it wasn't until Galileo, people knew the Earth was round, but they didn't believe that it spun, because they figured they'd just be flown off, because they knew how big the Earth was, and you should be spinning at 1,600 miles an hour at the equator. We should be flung off and we should feel this 16-mile-an-hour wind, and we don't. Okay, so again, the march of science is the march of against common sense. So you all familiar with the fact that the Earth is old, but it's younger than you think. So the Earth was formed about 4.54 billion years ago. 4.5 billion years ago, it was completely destroyed. When worlds collide, another planet called Theia slammed into the proto-Earth and completely destroyed it and the proto-Earth. Completely destroyed. Nothing left except a big liquid blob. And out of that big liquid blob formed what we now call the Earth and what we now call the moon. Okay? That's why we have a moon. It didn't make sense until the Apollo landings when we finally figured that out. So the question was, what was it like on the proto-Earth? Was there life on the proto-Earth? These are questions we'll never be able to answer. Okay, without a magnetic field, we would not be having this discussion. Without a magnetic field, the Earth would be sterilized. Plate tectonics, without plate tectonics, we would not have life. Without the carbon cycle, we would not have life. And by carbon cycle, I don't mean our current climate crisis. I mean the climate cycle that we just discovered 20 years ago that happens over millions and billions of years. So let's skip this. Yeah, all right. Let's skip this. I'm running out of time. Lecture number 4 is the sun. The sun is 93 million light years away. It's got a diameter of 100 Earths, and it's got a volume of 1 million Earths. Like I said, the surface is about 5,780 degrees. The center is about 15 million degrees. What drives the sun is thermonuclear fusion, which happens, actually it doesn't happen down the street, that's fission. Thermonuclear fusion is what happens in thermonuclear fusion weapons. So the sun rotates, the sun has a magnetic field. The magnetic field of the sun is why we get sunspots, it's why we get solar storms, it's why our power grid goes down when the sun has a hissy fit. And the sun has hissy fits on an 11-year cycle. Why is that? We'll talk about that. We'll talk about the lifetime of the sun. The sun's been around about 5 billion years. It's going to be around another 5 billion years, but that's irrelevant to us because our planet will be destroyed in about 1 billion years. Okay. And we'll skip this. The solar system, lecture 5. Our solar system was formed about 4.6 billion years ago. It consists of rocky planets, Mercury, Venus, Earth, Mars. It consists of gas giants, Jupiter, Saturn, Uranus, Neptune, and it consists of debris. This debris turns out to be important. Those debris includes asteroids that have our name on it, okay? So we want to find out about those. And then this is something we've only discovered in the last 10 years. Essentially, all stars have solar systems. Statistically, all stars have solar systems. We didn't know that. The first time we discovered any exoplanets was 1995, and then it was like 1 or 2. Now we've got about 6,000 exoplanet discoveries and about 20,000 in the pipeline. And statistically, all stars have exoplanets. This has just been an amazing statement. Pluto. I was told not to get political here. The question is, what about poor little Pluto? Here's the problem. So there's three places where debris happens. One is the asteroid belt between Mars and Jupiter. And you've seen that asteroid belt, see in Star Wars, where the Millennium Falcon has to go, yeah, right. Although the asteroids in the asteroid belt are separated by several million miles, but that's a detail. So we have the asteroid belt we're very familiar with. We have two other belts that we didn't really know about until the last 20, 30 years. The first one is called the Oort cloud, and this is a spherical cloud around our solar system. We can't see any objects in the Oort cloud. We know it exists, though, because that's where comets come from, and they come in from every direction, so we know the Oort cloud is spherical. And so when other stars pass by us, they perturb comets in the Oort cloud, and they sail into our solar system, and we see them, nice comets in the night sky. The third place for debris is called the Kuiper belt. The Kuiper belt is just like the asteroid belt. The belt between Mars and Jupiter, except it's past the orbit of Neptune. And it contains not millions of objects, but literally trillions of objects. And as our telescopes got better, we started discovering more and more objects in the Kuiper belt. It's far away, so it's very dim, so you had to use really powerful telescopes. The problem that started to happen in the 21st century was we were discovering objects in the Kuiper belt, and Pluto is a member of the Kuiper belt, that were bigger than Pluto. And we didn't know how long that would last. In other words, we didn't know if there were 10 objects bigger than Pluto in the Kuiper belt, or 1,000 or 1,000,000. And so if we kept Pluto as a planet, every time we found an object in the Kuiper belt bigger than Pluto, that would have to be a planet also. And so would you really want a solar system of 1,000,000 objects, plus, of which Mercury, Venus, Earth are that? And so the astronomer says, yeah, no. Sorry, Pluto. Bye-bye. That's why Pluto was demoted. And this is not the first time this has happened. In the 19th century, Ceres, which is an asteroid between Mercury and Mars and Jupiter, used to be a planet. But at some point people decided, yeah, it's a little small. And so it was demoted. And so we demoted Pluto. Pluto gets upset. In fact, let me show you how upset Pluto gets.
We've all come from a place, the entire human race depends upon Mercury, Venus, Earth, and Mars, Jupiter, Saturn, Uranus, Neptune. Sing along real strong for the next tune. Mercury, Venus, Earth, and Mars, Jupiter, Saturn, Uranus, Neptune. And I guess not Pluto.
I'm so sorry, Pluto. Okay, lecture 6. We've got the stars, how many, how far, how bright. We'll talk about the Hertzsprung-Russell diagram. So in chemistry, we have the periodic table. In biology, we have the tree of life. In astronomy, we have the Hertzsprung-Russell diagram, which actually wasn't invented by either Hertzsprung or Russell, but that's another story. So we'll talk about that. That's the way we organize stars. So again, I will send you the videos of this. That is a great video. I'd love to show it to you. We'll talk about the evolution of stars. Talk about black holes and neutron stars. We'll talk about the Milky Way galaxy. We live in an island universe that contains hundreds of billions of stars. And we'll make the distinction between the Milky Way, which is what you see, and the Milky Way galaxy, which is the collection of stars that we're embedded in, the different components of that, and the supermassive black hole at the center of our galaxy, and all of the hundreds of billions of other galaxies out there. And then we'll talk about the great discoveries of our universe that happened in the 20th century, the discovery of the Big Bang, the discovery of the cosmic microwave background, the discovery of dark matter, and then within our lifetime, the discovery of dark energy. okay? And these have completely changed our revolution of the universe. In particular, with the discovery of dark matter and dark energy, we then discovered that everything we thought we knew about the universe was 5%. 95% of the universe is stuff we know nothing about. And we'll be talking about that in lecture 5. So what we do know, the universe was born 13.8 billion years ago. It's expanded ever since. Most of the universe is dark matter. The laws of physics are the same for all space and all time. We do not know what dark matter is. We do not know what dark energy is. And we did not know why the Big Bang happened. And since I'm out of time, those are the 9 lectures. Thank you very much. I'm open for questions. Good questions will get bonus points. I actually do that with my students. Yes, sir. Yes. Yeah, I have I'll get into that in lecture 6. So what we do is, oh, I'm sorry, the question is, what else can you learn about a star? You know what the surface is made of, you know what its temperature is. There's lots of things. So in addition to all that, we have computer models. And the computer models tell us how a star should perform. And in fact, our computer models of stars means that we know stars better than we know people, because stars are relatively simple. And so we have a theory that a particular star should be fusing hydrogen, fusing helium, and maybe some carbon at certain temperatures. And then we predict what the outside of the star should be, like how big it should be, what materials it should be, what temperature it should be, and see if those predictions match up with what we see. Also, with some stars, we can use those Doppler oscillations to measure seismic waves in the star, just like you do in the Earth. You measure seismic waves to measure what the Earth is made of. You can do seismic wave studies of stars and use that to validate what the star is made of. You can use that Doppler shift to find out, is there another star or another planet going around that star? You can use those emission absorption spectra to calculate the magnetic field of the star. And you could also use your models plus those observations to detect how old that star is, what the future of that star is, how long that star has to live. You could also use the composition to figure out where that star came from. So for example, we've discovered stars in the Milky Way galaxy that, based on their composition, could not have been born here. They came from other galaxies. So it's just a phenomenal amount of information. I'll go over that in lecture 6. Yes, back there. So you're saying that, can you be succinct? I don't quite understand the question in there. Okay. I think what your question is, how are we sure that the electromagnetic radiation that we're observing maps reality and that the electromagnetic radiation hasn't been modified by dark matter and dark energy? Is that correct? Right. And so the question is, he's using the analogy of medicine where, like I'm on 15 drugs, I think. How do those drugs interact? And my answer to you, sir, is medicine is vastly more complicated than stars. That's not a joke. It really is. First of all, electromagnetic radiation has this wonderful thing where it doesn't interact with each other. So two electromagnetic waves can pass through each other. There's no interaction. If there was interaction, we would be able to see it. And that is, not only is that a fundamental observation, but it's a fundamental part of our theory of electromagnetic radiation, that it doesn't interact with itself. In terms of, and also if we're looking at, say, absorption lines, we're not looking at a single line. You know, hydrogen and helium might have hundreds of lines. And so we're looking for internal consistency of those lines. And so let's say dark matter or dark energy modifies part of that. We would see that modification. We would say something is messing up these lines in this frequency band. And that would win you a Nobel Prize, because that would be something. But that's the way we're always looking for internal consistency with what we've studied for hundreds of years. And when that violates it, we get a Nobel Prize. Yes. 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 I don't understand why I get this question every time I give a talk. The question was, how do we know that the 120 elements we know on Earth are the only elements? So first of all, every time we look at any corner of the universe, we see the exact same physical laws. So we see the exact same absorption emission lines, even for galaxies that are 13 billion years old, even things that are 40 billion light years away. So by observation, we see that the universe, the universal laws are the same in space and time. Now the question is the elements. So we know for a fact that the 120 elements must be the same throughout the whole universe. The question is, could different parts of the universe have elements of 130, 140 protons? And the answer is absolutely not. And the reason why is interesting. The reason why is, why does an element exist? An element exists because the nuclear strong force tries to pull neutrons and protons together. The electromagnetic force tries to push them apart. And so when you have a small nucleus, the nuclear strong force wins, okay? But as the nucleus gets bigger and bigger, the electromagnetic force becomes stronger and stronger. And the reason why is a little technical. The electromagnetic force has an infinite range, as you know. I mean, we live with the electromagnetic force. The nuclear strong force is a very short range. And so as the nucleus gets bigger and bigger, the infinite range electromagnetic force becomes relatively stronger and stronger. And that at that point where the electromagnetic force is so strong, you just cannot add more nuclei together. And so every element from uranium on is highly radioactive. In other words, it doesn't last forever. Elements that are from 110 on have lifetimes that's measured in nanoseconds. And we think the end of the line is around 120, 121. Nothing, just because of that balance. And so the periodic table we see is going to be exactly the same periodic table, except probably organized differently than any other alien. Okay, it's just that's the universe we live in. Yes. The question is living next to a high voltage power line damage to health? Absolutely not. There's no known physiological mechanism for that to happen, and there's no good evidence that it happens. There's lots of internet evidence, which is not evidence. You have to look at something. First of all, you have to look, does it violate basic physical principles? And secondly, if it violates basic physical principles, then the evidence for the effect has to be overwhelming, because what you're basically saying is there's an effect that's outside our current status of science. And that does happen. Every once in a while, such as dark energy, dark matter, we discover something that requires extraordinary evidence, and we collect the extraordinary evidence. The thought that high voltage power lines, which have radiation at 60 hertz, there's no known biological pathway for that to cause any effect, okay? And so that means the evidence for effect has to be at the extraordinary level, and I'm not even seeing any ordinary evidence for that. And so radiation has to be known as ionizing. In other words, a piece of electromagnetic radiation, for it to cause damage, with one exception, has to come in and spew electrons off of an atom, which makes the atom go wonka wonka. And that's what typically causes cancer, when you have atoms, especially in DNA, that go crazy. And that requires very high energy electromagnetic radiation. So that would require ultraviolet, X-rays, gamma rays. Visible light, certainly radio waves, don't have the energy. The only exception to that is, say, microwaves, which can't cause cancer, but what they can do is cause tissue damage by physically heating you up, by cooking you, okay? But that's it. Sorry. Other questions? Yes. Yeah, it'll cook you. Yeah, in fact, so the question is, radar sites which use microwave will cook. And in fact, the MiG-25, a Russian interceptor, which had a world-class radar on it, it could kill a rabbit at 100 yards. So yeah. So that's the exception. Other questions, comments? Yes, in the back. Thank you. The question is, how many brain cells will you form after 8 lectures? Enough brain cells you can apply to North Carolina State University. Hey. Thank you so much. I'll see you all next week.
All right, thank you.